Okay, so what is important about intermolecular forces? Remember, intermolecular forces occur between molecules. They're a force of attraction or repulsion between molecules. The first thing that they do is they determine the state of the molecules. Basically, the stronger the intermolecular force, the more likely you are to be a solid. The weaker the intermolecular force, the more likely you are to be a gas. Okay, so when in grade 10 we did those heating and cooling curves, that energy that we are supplying with heating, the kinetic energy supplied by heating, gives the particles more kinetic energy, and that is used to overcome the forces of attraction between the particles. So if we know what state the substance is at room temperature, it gives us an indication of the strength of the intermolecular forces. So what affects the intermolecular forces? One of the things is that the bigger the molecule, the stronger the intermolecular force. So for instance, if we look at the noble gases here, helium, neon, argon, krypton, xenon, if you look at their molar mass from the periodic table, it goes from 4 to 131. So xenon is clearly the largest molecule, and so larger molecules tend to have stronger intermolecular forces, and so this is agreed with by the boiling point. So this helium boils at 4 Kelvin. Now remember, this is not degrees C, this is Kelvin. So 4 Kelvin is almost absolute zero. Whereas xenon boils at 165 Kelvin, which is still not like anywhere near room temperature that it boils at. You really have to cool something a lot to get it down to liquid xenon. But you can clearly see 4, 27, 87, 120, 165. The boiling points are increasing as the size of the molecule increases. So we see this as well in not just the noble gases, but in the halogens. This is chlorine, bromine, and iodine, and as you know, chlorine is a gas at room temperature. Bromine is a liquid. You can see here there's some gas here, but there's definitely a little pool of liquid in this bubble. Okay, it vaporizes quite easily, but it is a liquid at room temperature. And iodine is basically a solid at room temperature. So in these little glass things, they will have heated up some gas and then sealed it off and broken the glass off to trap the three substances in there. And chlorine, bromine, and iodine are all diatomic molecules. They all share one electron, so they have the same kind of internal bonding, but chlorine is the smallest, iodine is the biggest, and iodine is more likely to be a solid at room temperature, is in fact a solid at room temperature. The next thing is density. Remember, density is the mass per unit volume, so it is the number of particles per unit volume. So if there is a strong force of attraction, the substance will be more dense. So I don't know if you've ever tried to float butter on water, but butter does not have that strong forces of attraction, so butter will float on water because it's less dense than water, because there are weak forces of attraction between the particles. The thing we look at the most is the boiling point and the melting point. So any energy that you put in to a substance to change its state, that energy that you put in is used to overcome the intermolecular forces. The intermolecular forces are kind of like a potential energy between the particles, and the moment the particles get more kinetic energy, the kinetic energy becomes stronger than the energy involved in the intermolecular force, and it separates the particles. So if you need to put in a lot of energy, then the melting point and boiling point are going to be very high. But if you don't need to put much energy in, the substance will change state easily because you are easily overcoming the intermolecular forces. So remember here, if we look at a gas, there are very weak forces. If we take energy away, the gas will condense to a liquid. So at the lower temperature, you will have particles with stronger forces of attraction. And if you keep removing heat, you will eventually get a solid. And in a solid, remember, they are closely packed. There are strong forces of attraction between the particles. So here we have to look at boiling point. What's the definition? Remember, it's the temperature at which the vapor pressure of a substance equals atmospheric pressure. And the stronger the intermolecular forces, the higher the boiling point. So here is an open system where there's evaporation. The liquid is turning into a gas as the particles bump into each other, and the walls of the container, they change their energies, and some of them go to gas. But if you seal the container and make a closed system, this is still happening. Some of the water molecules are bumping into each other, gaining energy and becoming a gas. But the rate at which the particles are leaving the liquid to become a gas, and the gas particles, are bumping into each other and losing energy and becoming a liquid, this is in equilibrium. The rate of them going to gas is equal to the rate of them going back to liquid. But when we boil a substance, the push of these particles is equal to the push of the atmosphere down on the surface of the liquid, and that's when all the particles have enough energy to separate out and become gas particles. So vapor pressure is the pressure exerted by a vapor, a gas, in equilibrium with its liquid in a closed system. So if you look at these two substances here, this substance is it's a pure substance, it's not a mixture, but you can see these little clear things, these little clear balls, there's a lot of them in the gas space. But if you look over here, there are very few of these little molecules in the gas space. It's got a low vapor pressure. So if something is got a smell that we can detect, and we open the lid and we can smell it, what we are in fact smelling are these vapor particles, the liquid particles that went into the vapor, and now when we sniff, they jump up into our nose and we can smell it. So usually if something's got a strong smell, it's got a high vapor pressure, and it's also very easy to boil because it doesn't take much energy to separate the particles from liquid into the gas particles. So obviously now, if you need a little bit of energy to go to your boiling point, okay, it means there's actually a high vapor pressure. So a high vapor pressure means a low boiling point, and a low vapor pressure means a high boiling point. It's an inverse relationship. So if you look at the different forces, remember London forces, sometimes called van der Waal forces, sometimes called induced dipole forces, okay, they are weak. Whereas a dipole force, like a hydrogen bond, remember when we talk dipole, it's permanent dipoles. These are slightly stronger, and hydrogen bonding, which is the strongest kind of dipole force, has got an increasing boiling point. So something that only has London forces has a low boiling point, and something that has hydrogen bonding has a high boiling point, because all of those opposite charges on the molecules attract each other and cause the molecules to stick more closely together. So in general, remember when we started looking at fluorine, chlorine, and iodine, the bigger the particle, the stronger the molecular force. But because hydrogen bonding is such a strong force by itself, it changes the melting and boiling point to make it higher than you expect. So for instance, if you look here, here's hydrogen bonded with oxygen, sulfur, selenium, and tellurium. And if you look at oxygen, sulfur, selenium, and tellurium, they're in a vertical column in your periodic table. The mass of the hydrogen is not changing. The nature of the bonding is not changing because they're all from the same group in your periodic table. Okay, so how come you would expect heavy with a high boiling point, slightly lighter, lower boiling point, hydrogen sulfide even smaller, lower boiling point, and then all of a sudden water, which is actually lighter than hydrogen sulfide because oxygen weighs less than sulfur, has suddenly got a massive boiling point, even higher than the heaviest one in this group. And that is because of hydrogen bonding. The electronegativity difference between the oxygen and the hydrogen is so great that water is a permanent dipole, okay, and that means it has a very high boiling point because there are strong intermolecular forces between water molecules. Also bear in mind that all of these, because they're the same group and have the same bonding, will have the same molecular shape. So you can't say, oh no, it's the molecular shape. All of these have got that lone pair on top. All of these are bent, but only the water has that huge electronegativity difference that makes it into a permanently polar molecule. So there's a strong dipole-dipole force that is stronger than ordinary dipole-dipoles. These are all ordinary dipole-dipoles, whereas this is hydrogen bonding, giving you a higher than expected boiling point. You can see this exact same trend when you look at the halides, the hydrogen halides. Hydrogen fluoride's the smallest, then hydrogen chloride, hydrogen bromide, and hydrogen iodide. Okay, so here's this water, sulfide, selenium, tellurium that we looked at earlier. And if you look hydrogen iodide, hydrogen bromide, hydrogen chloride, up to hydrogen fluoride. Hydrogen fluoride has got a way higher boiling point. Okay, bear in mind that it's actually 25 degrees, which is not a lot. But its boiling point is still significantly higher than hydrogen chloride and even bigger than hydrogen iodide, which is the biggest molecule, because it is got that nice hydrogen bonding between the particles, and then the boiling point is unexpected because small molecules should have a low boiling point, but this particular small molecule has a high boiling point because of the hydrogen bonding. You can see all of this trend carrying on here. Can you see this is oxygen, sulfur, selenium, tellurium? Here's antimony, arsenic, chlorine, fluorine, or this is the yellow dot, fluorine, chlorine, bromine, iodine. Here are the yellow dots, the halides, and then ammonia, this phosphorus with 3 hydrogen, arsenic, and antimony. They've also got this anomalously high thing, because here's the trend, here is the sudden high boiling point due to the hydrogen bonding. But if you look at methane and all of methane's partners in the same group, methane, CH4, does not have a huge electronegativity difference between the particles, and the molecule itself is not polar because it's a nicely balanced tetrahedral molecule, and the electronegativity difference between carbon and hydrogen is not that great. So this one follows the trend where here's a high mass, here's a low mass. The low mass has the lowest boiling point if there's no hydrogen bonding. Okay, and we will leave this there for now.